stood the test of time. And I originally give this historical lecture last year in the Festival of History. But before I dive into this story again, I want to tell a little bit more about myself and what I'm doing in DIAS. So as Krifa told, I'm a PhD student in the School of Theoretical Physics. This is me here, a bit younger, 2 years ago now. And then on the left of me, these are my co-workers. The left is Shane, a postdoc in our group. On the right is my supervisor, Graham. And on the far most right is another student, Kevin. And together we were working on quantum computing or quantum physics. And what we try to do is we try to come up with new state-of-the-art technologies. But actually we can't do our work, we couldn't do our work if some physicists in the past had contributed a lot. So like the two physicists I'm going to talk about here today, Schrödinger and Rowan Hamilton, they came up with some ideas that I still use nowadays in my research. So as said, this is like a historical lecture, and I'm going to describe the ideas and lives of these physicists in historical order. So I will start with describing Rowan Hamilton and his ideas in physics, who lived in the 19th century in Ireland. Then I will move on to Erwin Schrödinger, who was the first director of theoretical physics here in DIAS. And in the end, I will combine everything together to say a little bit about my own work and how these people influenced that. So to start with Rowan Hamilton, Sir Rowan William Hamilton was Ireland's most renowned mathematician. And you may wonder now, why mathematician? Like, aren't we here in the School of Physics today? Yes, that's true, but in the 19th century, it was still possible to do multiple topics at the same time, to be involved in different areas in science. And Hamilton was one of those guys. He worked mostly on physics and mathematics, but he also worked in astronomy and a little bit in chemistry and other subjects, because in this time it was still possible to do many things at the same time. But I am, of course, interested in his physics, so here today I will only spend time on describing his physics. To start with a little bit about the life of Rowan Hamilton. So he was born in 1805 in Dublin, and he lived here basically all his life until 1865. And only when he was a few years old, like 4 or 5 years old, he started living with his uncle in County Meath, in a village called Trim. On the left here, I show you the castle of Trim. And he lived there a few years to study languages with his uncle, because his uncle was a famous linguist. And he actually noticed that Rowan was also very talented in studying languages. And at the age of 13, it was said that Rowan Hamilton knew as many languages as the number of years in his age. So he was able to speak more than 10 languages at that young age, which is very remarkable. He was a born genius, if you ask me. So, but this is all to do with languages. Like how did Rowan Hamilton then get involved into physics and mathematics? To go into that, I want to tell you a little story that I found in the biography of Rowan Hamilton. Here on the left is the biography. It's a very old book. It's written in 1880. And I found actually this copy in a special collection in the DIAS building. And this special collection belonged to the former Irish president, Eamon de Valera. As you can see here on the first page of the book, it's signed by Eamon de Valera, which was a very famous president from Ireland. So I want to tell you the story in how Rowan got involved into mathematics. And this story was found in this book. And what I found was that he was involved into a maths contest with Sarah Colburn when Rowan was only 8 years old. And they brought the American child prodigy, Sarah Colburn, to Dublin to be in a competition with Hamilton for mathematical arithmetic. What this means is that they were given complicated sums that they had to solve in their heads, and then as quickly as possible give the solution. And Sarah Colburn actually was a child prodigy in the United States, and he was known as the living calculator. So that was his nickname. Like, he was so good at it that there was nobody on Earth that was better than him. And even Hamilton was not better than him, because Hamilton lost this competition by a huge difference, like a quite significant difference. And Hamilton writes in a few of the letters that I found in his biography that he was quite pissed about this loss. And because of this loss, he decided to spend more time on studying mathematics than studying languages. And this is how he got involved into mathematics. So then he went on to study mathematics at Trinity College Dublin. And also at the same time, he was still studying some languages as well in the college. But the professors in Trinity College, they soon recognized the enormous talent Rowan Hamilton had. And already at the age of 21, they decided to award him a professorship. However, there were not any professorships available at the time in mathematics or physics. So they decided to make him the Royal Professor of Ireland, or the Royal Astronomer of Ireland, sorry about that. So he became the Royal Astronomer of Ireland, which is a professorship in astronomy, which is again strange because he was a mathematician. But the idea these people had that awarded him this professorship was that it didn't matter what kind of position they gave Rowan, as long as it was a professorship, because then he was able to do the things he liked. So they gave Rowan the professorship and they told him, you can do the research you like. You can do whatever you like. You can spend it on mathematics, you can spend it on physics, you can spend it on astronomy, as long as he was making progress, and that was the case. So this was how he ended up as the Royal Astronomer of Ireland. And together with this position, he got a house, or actually you might know it, it's the Dunsink Observatory. It's given here in the picture on the left. And this Dunsink Observatory is in Dublin, and it is still in use nowadays. It's maintained by DIAS, and there's sometimes open days here. Of course, not now during the Corona crisis, but if you want to go and visit it, it's possible when the restrictions of the Corona get lifted again. But Rowan went here to live here in this Dunsink Observatory and spent the rest of his life here working on physics and mathematics. So that was a bit about the life of Rowan Hamilton. Now I want to move on to explaining some of the physics of what he did. And I want to do that in a way that I give like a little overview of what was known before that Hamilton arrived. So before Hamilton arrived in physics, there were a few different developments. One of them was the Newtonian mechanics by the British physicist Isaac Newton. And this has to do with the force of gravity. So how massive objects attract each other, like how things fall to the earth. You might have heard of the famous anecdote about the apple falling from the tree. This was done by Isaac Newton. Another theory that was developed at the time was the theory of heat, which is to do with how materials get hot and cold and how warmth is transmitted from one material to another. And then another interesting development is the theory of Fourier analysis, which was done by the French mathematician Joseph Fourier. And why was this interesting? So this all has to do with waves and time series. And if you do Fourier analysis, you get the characteristic frequencies of time signals and for example, sound signals. So you might remember a special technical device called an oscilloscope. Some of you might have had it at home or seen it in secondary school laboratories. But this device, what it does is it takes in, for example, a sound signal or a wave signal and then transform it into the characteristic frequencies of the waves. This is a bit technical, but it's a nice thing that was just developed before Hamilton came around. And now I want to go on to the time during Hamilton. So what happened during the time Hamilton was around? And there were a few different contributions by different physicists. One of them was by Thomas Young, a British physicist again, who figured out that light was actually made of waves and not of straight lines or rays. So this was done by a famous experiment by Thomas Young, the double slit experiment. And last year, actually, during the Festival of History, there was another presentation by a professor from DIAS, Tony Dorlas, and he explained this experiment. But the important thing I want to highlight here is that that light is made of waves and not of rays. And we will see and go back to this later in the presentation, why this is important. Then another development was the development of electromagnetism, because before the time of Hamilton, people thought that electricity and magnetism were two separate things. But thanks to the physicist James Clerk Maxwell in the Scottish man, he developed the theory of electromagnetism, which combines electricity and magnetism in one theory. And then finally, also there was some developments in thermodynamics, which has to do with how engines work and how engines apply work. And this also has to do with the theory of heat, actually. It's a bit of an upgrade. And one of the physicists that was working on this theory was a Northern Irish physicist, Lord Kelvin. You might have heard of him. So this is all nice and cool before Hamilton arrived, but what did Hamilton actually do himself? So let's go into that. So I have here a few different contributions. I can't name them all because he did a lot of work in his life. But one of the main contributions I want to highlight is the theory of Hamiltonian mechanics. And in the next few slides, I will explain a few examples of this. But it is actually a sort of mathematical upgrade of the Newtonian mechanics. So it describes the same sort of systems as Newtonian mechanics, but then in a more mathematical, neater format. So we'll go do that into a minute. But before that, I want to tell you about another contribution of Hamilton, which was the invention of quaternions. There is an interesting story related to this, because one day Hamilton was walking with his wife from his home in the Dunsink Observatory towards Dublin. And then at some point when he was passing the Broom Bridge, he had like an eureka moment and he said, "Quaternions, I have the solution." And he was so excited that he wrote the equations describing the quaternions on the Broom Bridge. And those equations, you can still see them today because they're still carved in the Broom Bridge, although they have been changed now in the form of a plaque. So if you want to go and visit it, it's possible if you go to the Broom Bridge in Dublin. And what is these quaternions? These are special numbers that are anti-commuting. What this means is, say you're probably familiar with natural numbers, like numbers 1 and 2, then you know that 1 times 2 is equal to 2 times 1. However, these quaternionic numbers are quite special because if you have a quaternionic number A and a quaternionic number B, then A times B is not equal to B times A, which is a strange property that Hamilton actually discovered. And if you want to learn more about this, Laurent Borston will give a lockdown presentation, I think next week if I'm correct, and he will tell a bit more details about this. So I would recommend going there if you're interested. And then a final thing I want to highlight is that Hamilton also worked on the wave theory of light, so that light is made of waves. And I have some dots here because Hamilton did much more work, but it's too much to mention here. But as said, I want to go into Hamiltonian mechanics because it's quite important for the development of quantum mechanics, which I will go to in the end of my presentation. So to make you a little bit familiar with this Hamiltonian mechanics, I want to give you a brief introduction into Hamiltonian mechanics, dynamics. And I want to do that based on a few examples. I think the best way to explain things is by examples, especially to a public audience. So I want to start with an interesting problem. And what I think is an interesting problem is given here in the picture. So probably all of you have come across this, this object, like these two poles, and then a chain hanging between the two poles. And I call this an interesting problem because a natural question for a physicist to ask is, why is this chain hanging in this particular shape? Like, why is it like bowed, or why is it like curved in this way, and why is it not straight or bent in another direction? And actually it is possible to solve this curve using the ideas of Hamiltonian dynamics. And to do that, in Hamiltonian dynamics, you need to know the total energy of the system, so the energy of this chain and the poles. And to explain that, I want to say there's two different types of energy in physics that we discriminate. One is the so-called kinetic energy, which is denoted by the capital letter T. And this is also known as the energy of motion. So any object that is in motion carries a certain amount of kinetic energy with it. And the equation for that is given here in the bottom, which is T is equal to a half mv squared. So that means that the kinetic energy T is proportional to the mass m of the object. So the heavier the object is, the more kinetic energy it carries. And also it's proportional to v, where v is the velocity of the object. So if the velocity is very high, is very high, then we get more kinetic energy than we have a low velocity for the same object. So that's the kinetic energy. Then there is another sort of source of energy in nature, and that's known in physics as the potential energy. And this is the energy in a force field. This is a little bit more technical than the kinetic energy, but the way this can be understood is that in nature there are lots of different forces. One of those forces is the gravitational force. You know that when something falls, it always falls to the earth or to the ground. And this is a direct consequence of the gravitational force. Like the gravity is pulling everything down. And the same holds for the chain, for example. Like the gravity is pulling it down such that it goes to the ground. And associated with this force, there is an associated energy, which is known as the gravitational energy, which is a special form of potential energy. Then there is actually another force acting in this system, because we see that the chain is not breaking, like it maintains its strength, like it's not torn apart into two pieces by the forces acting on it. And to explain this, there needs to be another force acting in this system, and that's inside the chain. And inside the chain, there is an elastic force, which makes sure that the chain doesn't break or maintains its shape. And also associated with this elastic force, there is an energy, and this is known as the elastic energy. So then what Hamilton did, or the Hamiltonian dynamics, is he was interested in the total energy of the system. And the total energy of the system is now given by the sum of these two separate energies. So we add up the amount of kinetic energy T together with the potential energy V to find the total energy of the system. And now with this knowledge at hand, its energy, we can actually find the shape of the chain, because it's known that anything in nature tries to minimize its energy. We try to, the configuration of the chain that is described here, this bow type configuration, is a configuration with the least amount of energy. And this is known. To do this, you can do this mathematically. I won't do it here because it's too technical, but it's known as the minimization of energy. So you have given the total energy, you try to minimize it, and then you will find exactly that the chain is given in this particular shape. So that was what I call an interesting example, but at the same time, it's a bit of a boring example because there's not much going on here, right? There is no motion, like this object is just static, it's not moving or anything. So to explain a more interesting example in which also motion is involved, I want to go to a second type of problem, which is a little bit more interesting and which I call a more dynamical example. So imagine for a moment that you are on the beach here and you're sunbathing with your partner. It's now again possible with this beautiful weather outside. So you are like in Clontarf Beach, for example, you are sunbathing here, and your child, he or she is playing in the sea off the shore for a bit. And at some point your child starts crying or screaming for help because it's drowning, it can't swim. And so the question is, what do you do? Of course, you want to go to your child and save it as quickly as possible. But what's the best way to reach your child? One way you could go to your child is by going straight into the water and then swimming to the same height as your child and then making a turn left and then swimming right to your child. That's one way. Another way is maybe more clever, is by walking first very far on the beach to the same width as your child, and then you swam straight the last bit to your child. That's another possible path from you to your child. And another way, which you maybe think is the best way, is if you just take the shortest distance. So you go directly from yourself to your child in a straight line, as given here. But the question is, what's actually the best way to do this? Is it like this path, or this path? So to come up with the solution to this, we can use Hamiltonian dynamics. And what Hamilton does is he tries all the different paths. So he tries this path, and this path, and then he assigns a weight to each of the paths. And the weight is more, in more mathematical terms, known as the action of the path. And this can be seen as some sort of score of the path. And this action depends on the energy. So the energy you need to go to your child, but also on the time. So there's two parameters, the energy and the time. And again, like before, we want to minimize, but this time we want to minimize both energy and time. So we want to minimize the action. And so in the more precise way, what Hamilton said is, we vary over all the possible paths. So we try all the different paths, and we obtain the solution path as the path that minimizes the action, that minimizes this weight. And then in a very formal way, the solution path is formally denoted as the x of t, so the position as a function of the time, which solves the equation of motion. This last remark is a bit for the people in the audience that are a bit more familiar with physics. But yeah, so the point is you can find the solution path in this way with applying Hamilton's variational principle. The name for this procedure is known as Hamilton's variational principle. And when you do that, you will end up with the following solution path. And that's actually, you go like on a bit of an angle on the beach, and then the last bit, you also go on an angle, you swim in an angle towards your child. So this is the solution. And actually, this is the solution of this problem. But the cool thing about Hamilton's principle is that it does not only hold for these examples. In fact, it actually can be generalized, and it holds to any classical mechanical system. What this means is that any system on objects that are in motion or moving, like the chain or you're running, something like this can be described by Hamilton's principle to find the solution of the paths. So this is quite a powerful theory, and it's actually still used nowadays. I still use it in my research, and it's also important for the development of quantum mechanics, as we're going to see in a bit. But before I go into that quantum mechanics bit, I want to tell you that this Hamilton's principle is actually very close to quantum physics already. It's actually, in fact, only one single mathematical procedure away from what is now known as quantum mechanics. So you then can naturally ask the question, like, why didn't Hamilton take this step? Why didn't he do this mathematical procedure and come up with the theory of quantum mechanics? Well, actually, at this moment in time, there was no reason or no physical motivation to make this step. Because as you remember in the overview of the different types of physics that were known at the time, theories that were known, as I gave earlier in the lecture, they just started discovering, for example, that light was made of waves. And also they didn't know at the time in the 19th century what an electron was. We'll see later, to have quantum effects, you need to go to the very tiniest scale of matter in the universe, which is on the scale of atoms and electrons. I'll explain in a bit what that means. But what it means here for Hamilton is that at this moment in time, there were no experiments that were seeing quantum effects. So people thought like, oh, Hamilton's theory is actually complete, it's valid, like it describes all the possible systems in nature. But we now know that was not the case. But the important message here is that theory and experiment go always hand in hand. Like if something is not invented in experiment yet, there is no point to come up with a theory. And if something is invented in theory first, then there needs to be experimental evidence to come up with a proof. So that's a bit, that was the story about Hamilton. Now in the second part of my presentation, I want to go on to Professor Erwin Schrödinger, who I call the Austrian that got hired by Eamon de Valera. Eamon de Valera, as said, was the former Irish president, and he was the initiator of the Dublin Institute for Advanced Studies, and he decided to write Schrödinger to come over to Ireland to be the first director of theoretical physics. And he did, and we will see now actually who this guy Schrödinger was. So again, like for Hamilton, I want to start with describing a little bit about the interesting life of Erwin Schrödinger. And to start with, again, Erwin Schrödinger. So he was born in 1887 in Austria, in Vienna to be precise. And Vienna was a very vibrant and cultural city at the time. And also Schrödinger became very culturally involved. But his family was quite interesting, because here I'm showing you a picture on the left of Schrödinger's family. Schrödinger was the only child of his father Rudolf and his mother here on the right. And he didn't have any brothers or sisters, but he had a lot of cousins in his family. And most of these cousins were females. One of them is shown here on the left. And it is actually said that, as we see later, that Schrödinger developed a special relationship with women later in his life. And it is said that this might have to do with the upbringing he had in a family full of females. So we'll see later why that's interesting. But it was also like Hamilton, Schrödinger was an enormous talent at a very young age. He was talented in a rich area of subjects. And like Hamilton, he was also interested in languages. And in particular, he was interested in poetry. And here on the left, I show one of the poems Schrödinger read in a school performance in secondary school. He attended Das Akademische Gymnasium in Wien, which is like the highest form of secondary education in the German system. And Schrödinger attended this, and at one point he gave a performance where he read this poem from Friedrich Schiller, a very famous German poet. But besides poetry, Schrödinger was talented in actually in any topic in high school. And he decided to go on and study physics in university, again in Vienna. And he became so good in physics that he was one of the fathers of the development of quantum physics. And for that, he won the Nobel Prize in Physics in 1933. And here on the left, I show you the picture for just before they got awarded the Nobel Prize. This is on the train station in Stockholm in Sweden. And these guys, three guys on the right, here on the outermost right, this is Schrödinger. Here, this guy in the middle is Paul Dirac, an English physicist. And then here, this guy is called Werner Heisenberg. He was a German physicist. You might recognize the name from a popular television series, Breaking Bad. Like the main character in the Netflix television series is named after him. So if you ever wondered who he was, it's a guy that also contributed to quantum physics. And so they won in 1933. But then afterwards, Schrödinger was living in Berlin at the time. It got, as you know, a bit of a hard time in Germany because of the Second World War. The Nazis gained power, and just before the war, Schrödinger actually fled Germany first towards Austria. He was spending a little bit of time in Graz for a while, and then afterwards also the Nazis took over Austria, so he had to flee towards first he went to Oxford in the United Kingdom. But he had problems in Oxford because he couldn't really get used to the way of living there. He was not feeling at home. And he was actually looking for another position, another place to live. And at that point in time, Eamon de Valera was looking for a first physicist to lead the Dublin Institute for Advanced Studies. And he invited Schrödinger to come over to DIAS in 1939. And here on the left, I have a picture of Schrödinger in his inaugural lecture in 1939 in the Royal Academy of the Sciences. So this was a bit of how Schrödinger ended up in Dublin. Now let's talk a bit about the life of Erwin Schrödinger in Dublin, because Schrödinger was living in Clontarf, and that's his house here on the left. It's in Kincora Road in the north of Dublin. And he was living in this house, interestingly enough, with his wife, Annie, but also with his mistress, Hilde, and the child that he had with his mistress. So he was living here with two different women at the same time. And we will see a little bit later a bit more about that. But actually what I want to tell you here in this slide is that this house was actually quite close to the beach in Clontarf, and Schrödinger liked spending time in the beach. He's like spending time outdoors. He was also a vivid cyclist, and he liked, one of the things he did was he cycled from his home always to Merrion Square, where the Dias building was at the time in the center of Dublin. And I want to pause here for a second, because later this year, because of the 80th birthday of Dias, we're gonna organize a cycle tour in which we start at the house of Dublin, of the house of Schrödinger in the north of Dublin in Clontarf, and we will cycle the same route towards the Merrion Square or the Dias building in Merrion Square. So if you're interested in this event, I would recommend you take a look into the Dias communication channels, and it will probably be hosted somewhere in the fall of this year. So that's a side note. The last picture in this slide actually is of Schrödinger in his later days in Dublin. Here he's already a bit older and he's actually retired. And he really liked it in Ireland. He would like to stay here, but in the end, he had to leave Ireland because his pension that he got from the Irish government wasn't sufficient enough to provide a comfortable living for him, his wife, and his mistress. So he couldn't afford living in Dublin anymore, and that's why he moved back to Austria and died there in Vienna in the 1960s. The reason he liked Dublin, I want to tell you here, is by giving you a quote that Schrödinger once made. So he said once, in Germany, if a thing was not allowed, it was forbidden. In England, if a thing was not forbidden, it was allowed. In Austria and Ireland, whether it was allowed or forbidden, they did it if they wanted to. So this was his view on Ireland. And one of the things I think he had in mind was that he was able to live with both his wife and his mistress comfortably without being looked after. So let's go a little bit tell a bit more about this. What's all this about? So Schrödinger actually had a very interesting view on marriage. He believed that bourgeoisie marriage, while essential for comfortable life, is incompatible with romantic love. What he means by this is that he liked having a wife to have dinner with, that cooked for him, that took care for him, and that he spent activities with, like walking and stuff. But he felt this was not compatible with his romantic interests. So aside from his wife, he felt he needed to go around and sleep with other women. And this was not like in an affair or affair kind of way, but he was completely open about this. And his wife knew about this as well. And also his wife actually, he was going around and sleeping with other men. One of the things was that his wife once was in a love affair with a famous German mathematician actually. So they all went around and slept with each other. But the interesting one is the wife that the second wife that Erwin actually ended up with in Dublin, because this was a woman named Hilde, which he impregnated when he was on his escape from Berlin towards Austria. And actually she was one of the wives of his colleagues. And he fathered a child with her, and that was the child that he was living with in Dublin. And also, as I said earlier, a little bit earlier, he was in Oxford for a while, but he couldn't really get used to the way of living there. And as you might know, Oxford is a very elite city or a village. And at the time, especially in the 1930s, it was very elite. And they didn't really like that Schrödinger went around with two women at the same time. So it was basically frowned upon, and Schrödinger couldn't get used to it. So that was one of the reasons he wanted to leave Oxford. So enough about this gossip and love life. Let's go back to the interesting stuff, to the physics, because we are here today, of course, for the quantum physics. And Schrödinger was one of the main developers of quantum mechanics. So I want to tell in the last part of my lecture a bit of what he did and how he contributed. And the main contributions he did for quantum physics were in the year 1926. And what he did was he was solving the hydrogen atom with the help from Hamilton. So let me explain what this means. So as you might know, all the materials in the universe are made of molecules, and molecules on their terms are made of atoms, and then atoms are again made of even smaller particles, which are called subatomic particles, such as electrons, or you might have heard of the Higgs boson. The Higgs boson was discovered in Switzerland in 2013. But the reason why this is important is because that the laws of quantum mechanics, they hold at the tiniest scales. So you start seeing quantum effects on the scale of atoms and even smaller. So electrons and the Higgs boson, for example. And at the time, just before Schrödinger arrived, they had the physicists around had developed a model for the hydrogen atom. Hydrogen atom is the main compound of water. And this model was developed by a Danish physicist, Niels Bohr. And he came up with the Bohr model. And I want to show you that here on the right, how that works briefly. So in this model, the atom is presented by a core, which is given here in the middle by orange. And then the electron in the atom is encircling this core in special orbits. You have this orbit here, you have this orbit here, this orbit. So you have different orbits. And this can be compared analogous to how planets move around the sun, but then on the very tiniest scale in atoms. And special about this Bohr model was that the orbits are actually fixed and have a fixed amount of energy that can be labeled. And the label is like n=1 for the first energy of the first orbit, n=2 for the second energy of the second orbit, and so on. So this was just developed before Schrödinger arrived. But the question at the time was, what were the orbits? Or they had an idea about the orbits. And what were the energies? And what Schrödinger did in his first paper in 1926 was he used the theory of Hamilton, the Hamiltonian dynamics that we showed you here earlier, that to find actually the energy of those electrons and also to find the paths or the orbits of the electrons. He found closed forms, or he found equations that describe the orbits of the electrons around the core of the hydrogen atom. And this was an interesting development, but this was not so groundbreaking yet, because there was still confusion. Like, people didn't know how an electron could go from one orbit into another orbit, while the energy of the first orbit was different from the second orbit. And they were thinking about that electrons were hopping from one orbit to another orbit, but this was a bit strange. Like, how could electrons hop from one place to another place? And to address this issue, Schrödinger came up with a second paper in 1926, only a few months after this first paper. And to explain the physics in that second paper, I want to go back a little bit to an important principle known as Fermat's principle. You might remember this from your period in secondary school, but this has to do with how light gets bent in materials. So here the yellow line is a light ray, and the two different colors of blue. One, we have light blue is one material and dark blue is another material. So say, for example, we have air here and we have glass here. And then when the light ray hits the glass, it gets bent or it gets refracted under a certain angle theta. So it gets bent by theta. And this is known as Fermat's principle by the French mathematician Fermat. And actually, I hope you see it here, but this picture looks very familiar to one of the pictures we saw earlier in the presentation. Because if you remember from the problem we did on the beach, this is actually very similar to Hamilton's principle, in which we varied over all the different paths and found the solution from you to your child. And actually, there is a direct analogy between Fermat's principle and Hamilton's principle. And Hamilton, already in the 19th century, was aware, like I said, he worked both in light theory and in mechanics, in Hamilton mechanics, and he was aware of this analogy. But another guy that was aware of this analogy was Erwin Schrödinger, and he knew that those two pictures were actually quite similar. But he knew more because he also knew that Fermat's principle doesn't hold if you go to the tiniest scale. As we said earlier, light is actually not made of rays. It can't be seen as straight lines, but in fact, if you would zoom in more and more, you will see that light is made of waves. So this picture of Fermat's principle doesn't hold on the smallest scale, and therefore it breaks down. Now the question that Schrödinger asked was, is the same happening in Hamilton's principle? If we zoom in and we go to tinier and tinier particles, does the same happen? Like, do we need to describe the smallest particles by waves instead of the standard Hamiltonian dynamics? So the question was, does it break down at the smallest scale? And it does, that we know nowadays. And this was what I addressed Schrödinger in the second paper. But to describe particles as waves, you need to have an equation that describes waves and not like the standard Hamiltonian dynamics equations. So in the second paper, I've given here a fragment of that paper. Schrödinger developed a new kind of equation that describes particles as waves, which is given here in the box. It's of course a bit technical, but you might recognize this equation because it's written now on front of the Dyas building in Burrington Road in Dublin, because this is nowadays known as the famous Schrödinger equation that describes how quantum systems evolve forward in time. So how the dynamics of quantum systems. And this is a wave equation because particles are described by waves. So this was one of the main inventions of Schrödinger. And it's actually one of them that I use nowadays in my research almost every day, at least a few times a day. And this is this is one of the most important ingredients in my research. And it's so important that Schrödinger, as said, he won the Nobel Prize in 1933. And that was one of the main things for this was this paper. But he did more things. So I want to jump forward in time to after his Nobel Prize. And I want to describe the Schrödinger cat thought experiment. You might have heard from this in popular media, like it was on television a few times in a few movies. For example, in the Big Bang Theory, Sheldon explains Penny at some point what the Schrödinger cat thought experiment is, if you have seen that television series. But what I want to do here is explain it correctly and what it is actually all about, because it's a very useful thought experiment. And Schrödinger came up with it because he was writing a lot at the time with Albert Einstein, and Albert Einstein was also into these kind of thought experiments. What I mean by thought experiment is that it is something in your head, like it's not a real experiment. It's just something to describe a theory. So how does this work? Well, we have a cat inside the box, given here on the right. And together with this cat, we put a mechanism in the box that is able to kill the cat. So for example, we have this bottle of cyanide here. And when this bottle of cyanide breaks, the cat dies. And we connect this bottle of cyanide or this mechanism to a quantum device. This is important. So for example, we connect it to a hydrogen atom in which an electron is able to move around the core, as we saw earlier. And say now, if an electron hops from one orbit to another orbit, the bottle of cyanide breaks and the cat dies. So that's the setup. And Schrödinger is actually looking from the outside. But from outside, you can't see inside the box. He doesn't know what's going on. For example, an electron could hop from one orbit to another orbit, and then the cat dies because the bottle of cyanide breaks. But Schrödinger is looking from the outside and has no idea that it happened. So from the outside, he is confused. He can't tell if the cat is now dead or if the cat is alive. So the solution for this problem that people came up with the theory of quantum mechanics is that the cat can in fact be considered to be both dead and alive at the same time. And in more mathematical terms, this is known as the superposition principle. This means that the cat can be in a superposition of multiple other states, of a dead state or an alive state. And that's given here in this equation. So there is, like, for example, a half probability that the black cat is alive, or there is a half probability that the black cat is dead. So in fact, it's both dead and alive at the same time. Of course, this doesn't happen in real life because cats are too big to be considered as quantum objects. Quantum objects, as said earlier, are on the scale of atoms and smaller. Therefore, it was important that we had this quantum device in there of an electron hopping from one orbit to another orbit. But in fact, the thought experiment really holds. Before I finish off my presentation, I want to give you a little bonus about a more advanced concept that I use nowadays, and also that Schrödinger actually came up with in shortly after 1935. And I want to explain that by using two cats. Say now, for example, we have a black cat on the left here in the box and a red cat on the right here in the box. And we can't look inside the boxes, and there is a mechanism with the cats that is able to kill them. And we don't isolate the boxes fully because the cats are still able to interact with each other. They're still able to talk with each other. And because of this interaction, after some time, they end up in a special superposition state in which there is a half probability that the black cat is dead and the red cat is alive. And there is a half probability that the black cat is alive and the red cat is dead. So this is the state that this complete system of the two cats is in. But now what we're going to do is we're going to take the boxes apart. We're going to bring the red cat to the right here, and we're going to bring the black cat to the left. And now what we're going to do is we're going to open the box of the red cat. And then we're going to see, of course, if the cat's dead, or if the red cat is dead, or if the red cat is alive. If we open the box, we see, for example, that the red cat is still alive. And then we can say immediately something about the other black cat, because we know that the system was, or these cats were in this special state given here, and there was a half probability that the red cat was alive, and then the black cat is automatically dead. So by opening the box, we see that the red cat is alive. We can immediately tell by this equation that the black cat is dead without opening the box of the black cat. So this is quite mysterious. And this is actually a property in quantum physics known as quantum entanglement, some long range correlations going on. And this is an interesting concept. And it's actually still researched nowadays a lot in current physics. Yeah, so that was Schrödinger's contribution. And to end my presentation, I want to tell you a little bit about what I did, of course, or what I do. What I do now is I use these ideas of Erwin Schrödinger and Hamilton, so the Hamiltonian dynamics, the superposition principle, to come up with new technologies. Technologies like quantum computers or quantum devices. And the advantage of these technologies is that they are much faster or much more powerful than the standard technologies that you know. For example, the laptop from which you're now watching this presentation is much more, is very slow compared to the future quantum technologies. And the reason that quantum technologies are better is because they are able to make use of these advanced concepts like quantum entanglement and the superposition principle. So in my research, I use these ideas of Hamilton and Schrödinger to design these new futuristic technologies. And to end my presentation, I want to give a short summary then of what we did and learned here today. We started off with describing the life of Rowan Wilhelm Hamilton, and we looked into the total energy of the system given by the Hamiltonian. We looked in the Hamilton's principle, which was this varying over all the different paths. And then we looked into Schrödinger's life, his wave equation that describes quantum particles as waves. We looked into the Schrödinger cat experiments and the quantum entanglements. And here in the box on the right, I have new technologies, which is what I am working on today. And that's the end of my presentation. Thank you very much.
Thanks a million, Luuk, for that very informative presentation. If anybody has any questions, feel free to pop them into the chat bar there at the end. One thing I think that you didn't include in that, Luuk, was the fact that Schrödinger actually became an Irish naturalised citizen over the course of his time in Ireland, which I always find kind of interesting myself. I just have a quick question, actually, if that's okay. And again, I am by no means any physicist, but kind of going back to your quantum entanglement, the cat's images that you had there. Is there a possibility within that equation, or is there an equation where both cats are dead at the same time, or does that just bring it back to the initial kind of quantum mechanics point?
Sorry, so your question is if there's a possibility that
both cats are dead. So within that equation, you have either one cat is dead at any given time, but I suppose, is there a possibility that both cats are dead if you open the box?
Yeah, there's also a possibility that both of them are dead, or both of them are alive at the same time. Yeah.
All right. Okay, and the equation just remains the same regardless?
No, the equation actually, yeah, that's important. So this equation changes depending on the interaction that's going on between the cats. So this is just one particular example, but you also have more complicated examples in which actually the red cat is both dead and alive, and the black cat is both dead and alive. So you have very complicated situations.
Yeah, it's a little bit beyond me, definitely. Okay, well, just as we're kind of waiting to see if there are any more questions, I just wanted to first and foremost thank you all for attending today, and obviously thanks to Luuk for that very informative presentation and talk. Also to let you know that our final lecture will actually take place this Thursday on the 11th of June. Thankfully, Ireland has moved into phase 2 of lifting the restrictions, so the lockdown doesn't really exist to the extent it did originally. Our final lecture is from somebody who was very recently formally part of the School of Theoretical Physics. He only left at the end of 2019. Dr. Leon Borston, as Luuk mentioned earlier, and his talk will be titled "The Road from Dunsink to 11 Dimensions." So I think, I could be totally wrong, that it could kind of tie in both what Luuk has spoken about and what Samuel talked about in our talk last Thursday. Also to highlight that we do have a Bloomsday event taking place tomorrow evening at 7:30, again via Zoom, and it will incorporate kind of aspects of Ulysses will be read by an actor. We hope to have a virtual tour of Dunsink Observatory at that time as well. And there will be talks as well from a number of different people, just I suppose on the science behind Ulysses. So that's we've got some tickets left for that. I think there's about 10 or 12 tickets left for that. And then the following week we have a panel discussion taking place, because that brings us into our Dias anniversary week. So the act itself was signed on the 19th of June in 1940. So over the course of the 15th to the 19th of June, we'll be running a number of campaigns, obviously on our social media, but we have 2 kind of big events that will take place. So on Monday the 15th, we will have a panel discussion that will explore, I suppose, the relationship between Dias and our founder, Eamon de Valera, which Luuk has put on today. And then on Friday, which is the 19th, and Dias Day itself, we will have the Dias Day lecture. And full details of that will be made available on our website and via our Eventbrite in the coming days. So before we finish up, Jeff has one question there, Luke. I don't know if you've had a chance to have a look at it. He wonders, Hamiltonian's quaternions equations are used by 3D video games these days. Any idea what would a video game based on quantum equations look like?
Ooh, that's a bit, that's an interesting idea there. So a quantum game, depending on quantum equations. Actually, interestingly enough, there is some games already out there, things like quantum tic-tac-toe and quantum chess, and they use these special properties like superposition. Like for tic-tac-toe, you could be in in normal tic-tac-toe, you could be in a certain position, but then in quantum tic-tac-toe, you could be in multiple different positions at the same time. So I think games would look like that then. But then, of course, the important thing is, this is a bit, quantum theory is, it's theoretical. Like we don't observe quantum processes directly. Like we don't see cats that are dead and alive at the same time. We can only put some equation on it, and then we see that it's actually dead and alive at the same time. But when we go in and open the box, it's either dead or it's alive. So in a game, I would expect it's the same. It's either, you will see it either dead or you see it alive. But you could make, of course, an hypothetical game in which it is possible to have superpositions and quantum entanglements.